Next there was some shared like with a big table and then
Okay, so hi everyone and welcome. How many of you already started the exercises? Great. And do you have any questions, problems? Everything good?
to end it off saying I think it's problematic if you don't know the distribution.
Yeah, it's a tricky question. Just think of it and just write what do you think is the right answer. Okay, we know it's a tricky question. More questions? Okay. So today we will continue the probability review that we did last week in the first hour, and in the second hour we will talk about a decision between two world states, as you saw in the class. So let's start. We will talk first of all about special distributions. So the first and maybe the simplest distribution is the Bernoulli distribution. So we say that any binary random variable that can get values from the set 0 and 1 is called a Bernoulli variable, and we denote it. It is denoted as X distributed Bernoulli with some parameter p. Okay? And what is the distribution of X? P of X is equal to okay, 0, okay, 1. What is the probability to get 1? Right. And the probability to get 0? Right. Okay, and the expected value of X is P also, right? And the variance of X is P1 minus P. Okay. You can do it. It's very easy to see. So now let's suppose that we have n such Bernoulli random variables, x1 to xn, and each one of them is Bernoulli random variable with some parameter p, okay? And they are also independent. That means that they we call them IID, okay? IID. Tali already mentioned it in the lecture. And now we want to look on some new random variable. We define new random variable, x is equal to the sum over all the random variables, the sum of xi. So in this case, we say that x is a binomial random variable. Binomial random variable. And what is the distribution of x? What is the distribution to see a specific path, a specific sequence? Like, for example, to see a k 1s and n minus k 0s? No. What is the probability to see 1, 1, 1? To see 1. What is the probability? The probability to see 1 of Bernoulli random variable is p. Only p, right? What? So now, what is the probability? What is the probability to see p k 1? To see k times the same value? Just p to the. It's right for the first question. Just p to the k, right? To see the probability to see k1 is just p to the k, to the power of k. And what is the probability to see n minus k zeros? What is the probability? Right, 1 minus p to the power of n minus k. Is it clear? No, exactly k. Yeah. Because they are independent, it's just the multiplication of their.
You also have to consider all the cases where it's not.
So just a second. For for a specific sequence, when I tell you that in the first place we got 1, in the second place we got 0, etc., the probability to see k 1 and 1 minus k and n minus k zeros is this probability. Okay? For a specific sequence. But now we have a lot of sequences. So basically we need to choose k sequences out of n elements. Therefore, we have n choose k possibilities. Do you know this term, n choose k? It's just n factorial divided by k factorial times n minus k factorial. Okay, is the number of options to choose k elements out of n elements. So this is exactly the probability of x. Okay? This is the probability of x to choose that x is equal to k. Questions? Okay. Do you understand why I need this factor of n choose k? Yes, no? Okay, so a good exercise if you want is to check if this if the probability of this is also it's normalized to 1, so you can prove it. It's very simple. You can prove it by the binomial formula. Now let's see what is the expected value of x. So what is the expected value of x? The expected value of x is the expected value of the sum over all xi, right? This is the definition of x. And because the expectation is linear, we can replace the sum with the expectation, and we got that xi, and this is equal to n times p. Okay? Now let's see what is the variance. So what is the variance for sum of independent variables? Right. So it's the sum of the variance to n, the variance of each one of them, and we get that it's n times p times 1 minus p. Okay? Good. Now let's talk about Poisson distribution. So the Poisson distribution is used to model the number of times that a certain event has occurred. Okay, for example, if you are from LSEC, the number of times that a neuron emits or fires in 1 second. So we denote. So the random variable x is distributed by the Poisson distribution with some parameter lambda. That this parameter is the rate of the event, and of course, and lambda can be only bigger than 0, and the distribution of it is so the distribution, the probability to see k times this event is lambda to the k divided by k factorial e minus lambda. Okay, and when k is between can be 0, 1 to infinity. Okay. K. K. Okay. K is the number of times that we see the event. So let's see what is the expected value of the Poisson distribution. Lambda, right? Let's see why. So the expected value is equal to, right, sum over all the k's between 0 to infinity, k times lambda k to the k divided by k factorial e minus lambda. Okay, this is the definition of the expectation. And you can see that if k is equal to 0, all this equal also to 0, so we can start from k equal to 1. And if we divided k with k factorial, we get k minus n factorial. So at the end, we get k from 1 to infinity. We can, okay, lambda times k minus 1 divided by k minus 1 factorial e to the minus lambda. And we can change the name of the variable k. We define new variable L that is equal to k minus 1. And we get that it's equal to lambda sum over L between 0 to infinity, lambda to the L divided by L factorial e minus lambda. And what is this term? What? 1, right. This term is 1, and we get that it's lambda. Okay? Great. And you can also prove by the same trick that the variance of Poisson distribution is right, lambda. So the variance of x is equal to lambda. Okay? Great. So now let's do a small example. Okay. So so now the question is, what is the distribution of the time interval between two events that distributed with Poisson with a parameter lambda? Yeah. Okay. So we have two events. For example, one event and some event that occurred at time t. And we want to ask, what is the distribution of the time interval between these two events? So, how can we do it? So, the first event occurred at time 0, right? The second event occurred at time t. Now, let's define, basically we are interested in the distribution of t. Okay, this is the question. What is the distribution of t? So let's define xt as the number of events that occurred until time t, small t. Okay, so how xt is distributed? Poisson with? No, because we sum over a lot of we sum over t time intervals, timestamps. So it's lambda t. Okay? Do you understand why? No. So okay. So in one timestamp, what is how Poisson how our events are distributed? Poisson with lambda, right? So if we want to check how many events has occurred in t timestamps, what is the total rate? Right, it's lambda t. So xt is distributed as Poisson with lambda t. And now we want to ask what is the probability that there were no events until time t? What is the probability that t, basically the t is here, okay? Because this is the first event, and we want to ask what is the probability that there is no event till this till t. So t is here, small t is here. So what is the probability of this? is the probability that xt is equal to 0, right? Okay? You are with me? Okay, so what is the probability that big T is larger than small t? Is the probability that xt is equal to 0. And what is this probability? Right. Why is that? Because this is equal to e minus lambda t times lambda t, which is 0, divided by 0 factorial, and this is equal to e minus lambda t. Okay? And what is the probability that t is smaller than, that big T is smaller than t? What is the probability?
1 minus?
Right. 1 minus this term. So it's 1 minus e minus lambda t. Okay? So this is the CDF of the distribution. You can take you can derive it and to get the probability distribution. Okay.
Can you repeat what is the capital T?
Capital T is the time. Is the time that the second event has occurred. Okay. The first event is at time 0. The second event is at time capital T. And we want to ask what is the distribution of the time interval, how the time interval is distributed between these two events. Okay? Okay, so someone know what is this probability? So this is the CDF of the exponential distribution. So the exponential distribution, so for a random variable, x is distributed with as exponential distribution with some parameter lambda. Lambda is bigger than 0, and the density function of it is equal to lambda e to the minus of lambda x if x is at least 0 and 0 else. Okay? So this is the definition, and it's the first continuous distribution that we see. Okay? And you can also show that the expectation of it is equal to 1 over lambda, and the variance is and the variance is 1 divided by lambda square. Okay? Great. Now, this is the CDF. If you take the integral of it, you will get this one. Okay, now let's talk about maybe the most important distribution, the normal distribution. So, the Gaussian distribution. So we say that x is distributed as Gaussian random variable with two parameters, mu and sigma, and if it has the density function of 1 over 2, square root of 2 times pi sigma to the square times e minus x minus mu to the square divided by 2 sigma to the square. Okay? I assume that all of you already know it. And what is the mean of the random variable? What is the mean of x? Right? And the variance? Right. So the mean of x is mu, and the variance is sigma to the square. Okay? And it looks like that when here it's the mean. Okay, this is the bell shape that we already know. Okay, so this is the Gaussian distribution, and now we'll talk about some important properties of it. So the first one is a normality. That the Gaussian distribution, if we have x, is distributed as random variable, as normal random variable with some mean and variance. And we define y is equal to ax plus b, where a and b are some constants. What is y? What is the distribution of y? Yeah, right. It's normal with a mean of, what is the mean? Right. And the variance is? Right. So y is distributed as normal distribution with mean of a mu plus b and variance a to the square sigma to the square. Okay? The second property is standardization. So we have, let's suppose that z is a normal distribution with zero mean and variance of 1. Okay, it's the normal distribution. And now we have some other Gaussian random variable, and we want to change it. We want to shift it to a Gaussian with zero mean and sigma to the square 1. So how can we do it? Apparently that z is equal to x minus mu divided by sigma. Okay? And this is distributed as normal Gaussian with zero mean and 1. Okay, with standard normal Gaussian. Okay, so give me some random variable with Gaussian distribution, and if you reduce the mean and divide it by the STD, you will get a Gaussian with zero mean and variance. So this is very useful because why? So why is it useful? Because what is, if I have random variable, Gaussian random variable x, what is f of x? I can define f of x in the terms of the normal Gaussian, the normal distribution, but just shift the mean and divide it by the variance. So f of x, f of x is equal to, by the definition, right, to all the values that is smaller than x. And if it's not here, but if z is equal to x minus mu divided by sigma, I know that x is equal to sigma z plus mu. Right, I just substitute here, and this is, I know that this is equal to z, all the values of z that is smaller than x minus mu divided by sigma, and I can write it as this is a function of the standard normal distribution. Okay? So I can write it as with some write it as phi of x minus mu divided by sigma. Okay? So for every random variable, Gaussian random variable, I can change it to the CDF of the standard normal distribution. And what is the sum of, so this is the second property. The third property is what is the sum of independent random variables. So if we have x1 to xn, all of them distributed with mu I and sigma I, what is the sum of them? The random variable y is equal to the sum of all the xi. How is it distributed? Right. Normally with the sum of their means and the sum of their variance. So okay? If they are, sure. Yeah. It's very important, because if they are not, it's not true. It's not even Gaussian. Okay. So this is a Gaussian random variable, and now let's talk about multivariate random variables. Multivariate. Okay, so we didn't talk about multivariate random variables, but basically the same. A regular random variable is a function between the sample space to R, and here we have a function from the sample space to Rd. Okay, we have a D component of the random variable. So multivariate normal distribution, we define it by, so now we have a vector, random variable that it's a vector, and we say that it's distributed with as normal distribution with some vector of mean and covariance matrix. Okay, now we have vector of mean and some, instead of the variance, we have a covariance matrix. And so what is the mean? What is this? What is the mean of all the? What is the mean of this multivariate random variable? So, as I said, we have here for each component of the variable, of the random variable, the I component of this vector is the expectation of this component. Okay, so here we have a vector of expectation. So it's 1, 2, 2, x, n. Okay? And the covariance matrix is defined by, so the covariance matrix is just the covariance of covariance matrix xj is the covariance of the I component and the j component. Okay? So the covariance matrix, what is the value? What are the values on the diagonal? No? The variances, right? The variances of the component, and what is how each of the component is distributed. Xi is distributed as normal distribution with mean mu I and sigma II. Okay? Each one of the components of X is normal. What? No, it's not definition. This is definition. This is definition of the normal distribution, of multivariate normal distribution. But it's very easy to show it.
No, I'm just wondering, like, when you define the multivariate normal, what does it mean? The PDF?
Just a second, I will get to the PDF. You can define it also by the PDF.
How do you define it? Because first you talked about, I'm not sure how to translate, but you talked about for one variant.
We said, okay. So,
Versus PDF.
yeah, okay. So I will get to the PDF of multivariate, but we just say that a multivariate, if a multivariate is a normal, if a random variable is a multivariate normal distribution with vector of means and covariance matrix, then the mean of this random variable is this vector, and the covariance is this. Okay? That's all what I said. Okay. Now let's go to the PDF of it. So the density function of X is 1 over square root of 2 times pi the norm of sigma E minus half x minus mu transpose the inverse of the covariance matrix x minus mu. And okay, so this is the density function of the multivariate random variable, a normal random variable, and as you can see, it's basically it's just an extension of the regular normal distribution, but instead of means we have vector of mean. Instead of the mean, we have a vector of means, and instead of the variance, we have a matrix.
What's the small sign on the left?
Half. Minus.
I'm not sure if it's just the mark from before or the inverse of sigma.
This is the inverse of sigma. Yeah.
Why?
We are why the this is the definition. This is the definition. In the normal in normal distribution, the regular normal distribution, we have here divided by sigma, right? It's the same intuition. But we are assuming here that that we can do it. It's invertible. That this matrix is invertible, but it's not by the definition, but it's some assumption that we are doing here.
Isn't it symmetric?
It's symmetric, but it can be positive. It's not. It can be semi-positive and not positive. Yes.
Is it sigma in the absolute value?
Yeah, it's the norm of the sigma. Sigma here is a matrix.
Yeah.
Yeah. Okay. More questions?
Yes.
Yes.
So x here is a vector?
Yes. Yes. X. Okay, because we have for each component of x, we have it's the size of the dimension of x.
And
Because it's multivariate. We have several of dimensions. What?
I'm asking the rectangle.
Okay.
Can you give an example of
For a normal.
no, for the multivariate. When can you like just an example?
Basically, the intuition is just a normal distribution in every channel, in every dimension. This is the intuition. We will see a lot of examples during the course. We will use it a lot when we talk about information and entropy. Okay. Cool. More questions? Okay, we have. No, you know what? Okay, let's do a break and we'll start. Okay.
מה שיש לקרוא זה נכון?
מה שיש לך פה, לא, זה וקטור.
זה וקטור.
יש לך.
וקטור הזה?
כן.
ואז יש לי E בחזקת וקטור?
כן.
אז זה כאילו הטור טיילור, נכון?
זה לא, מה זה טור טיילור? זה ה...
מה זה E בחזקת טיילור?
לא, מה זאת אומרת? זה לכל קומפוננט. זה לכל... יכול להיות שיש לי את זה פה גם? בעיקרון, לכל...
אני לא מבין מה משמעות, כאילו, של X.
לכל... יש לך... זה וקטור, זה סליחה, זה סקלר, כי לכל יצר בעצם הדיסטריביושן. אוקיי, בואי נראה את זה. יש לך משתנה גאוסי רגיל, בסדר? הוא לוקח לך בין הסאמפל ספייס שלך, נכון? ל-R, אוקיי? ה-probability function לוקחת מ-R היא לוקחת גם בעצם לזה של בין 0 ל-1, נותן probability, אוקיי? במקרה של בכלל multivariate, במקרה הגאוסי זה גם נכון, יש לך פה בין הסאמפל ספייס שלך ל-RD, בסדר? והפונקציה הזאת, ה-probability function זה probability, וכאן ה-density function לוקחת מ-RD והופכת גם עדיין ל-0-1.
השאלה אם פה צריך להיות, אם פה זה וקטור או פה זה x1?
פה זה וקטור, לא, פה זה וקטור.
אוקיי, אז...
תחשבי, זה וקטור, זה וקטור.
אני מקבלת וקטור.
נכון, ואז
טרנספוז של... זה סקלר.
נכון.
זה סקלר. עכשיו, מה יש לי פה סקלר?
כן.
נכון.
זה הנורמה של המטריצה. בסדר? את פשוט לוקחת, את נותנת מספר, מה ה-probability שלך לראות את הדוגמה הזאת, שב-x1 יהיה לך איזשהו value, עד xn יהיה לך איזשהו value. מה ה-probability לראות את הוקטור הזה?
אז זה כאילו ההסתברות המשותפת לכל הוקטור.
כן, בדיוק. עכשיו, את יכולה...
אני יכולה לדבר כאילו על ה-conditional?
בדיוק, את יכולה לדבר, בדיוק, את יכולה לדבר, ואם הם בלתי תלויים זה כמובן הכי קל, אבל ברוב המקרים הם לא בלתי תלויים.
זה ההגדרה כאילו?
כן, זה של הגאוסי, כן. זה ההגדרה של זה.
אז אני לא צריכה שלי. אני זוכרת בזמני סטטיסטיקה פסיכולוגית.
כן.
אבל שהגדירו את זה ככה שצריך שכל המרג'ינל יהיה נורמל ושכל הקונדישיונל של אחד על השני.
את יכולה, זה לא משנה, זה כמו שאת יכולה, זה אותו דבר, כן. אם את מגדירה את זה, את מתקבלי את זה, אם את תגדירי את זה באמצעות המרג'ינלס, את תקבלי את זה. זה קצת יותר מסובך לעבור משם לשם. כאן לכאן זה קצת יותר פשוט לעבור.
גם נובעים, כאילו שאם אני לוקחת את xi על xj, אז גם יהיה נורמל?
רגע, עוד פעם, מה את אומרת ש-p של... או f?
f של...
f של מה? xi?
נותן איזשהו ערך של
xk של... כן. xk שווה איזשהו... כן.
כן, אז זה גם יהיה נורמל?
לא, אני חושב שלא, conditional כל שאר כל שאר כן, כל שאר זה שלך.
אבל אם אני עושה על כל השאר זה עדיין יהיה...
כן.
אז אני מצטער לשבת זה מה שאני מכירה.
כן.
ואז את גאוסיאן ב-X נניח, גאוסיאן ב-Y, גאוסיאן ב-Z, אם כאילו מדבר על המערכת או משהו.
באינפוט הפוך שאני יכול לשים קונגרסון מסוים בתוך אני יכול להכפיל את שם בסוף ב-Y ולהגיד שוואי זה משהו, כאילו מה שאני יכול לעשות, להגיד שזה האינפוט בפונקציה, זה לא במשמעות במובן שזה לא מכריח אותי ללכת על שני חשיבה משנה. אני יכול להכפיל את זה בסוף פה עוד משתנה, שהוא לא נמצא פה רגע. זה קושי, הוא לא חייב להיות בתוך האינפוט, הוא לא חייב להיות. בעצם אני רואה קצת ספציפית, אני יודע מה אני אני לא מבין את המשמעות של להכניס X וקטור לקבל מספר בסוף.
אתה לא מבין את המשמעות של מה?
להכניס וקטור לקבל בסוף מספר.
תחשוב על זה שיש לך, אני רוצה לדעת מה הסיכוי, יש לי פונקציה, נגיד שהיא דו-ממדית, בסדר? יש לי איזושהי פונקציה דו-ממדית, ואני רוצה להבין מה הסיכוי לקבל בממד אחד שלה את הערך הזה, ובממד שני את הערך הזה.
אבל ההתפלגות היא דבר על כל הערכים שלי.
היא על כל הערכים בכל הצ'אנלים שלי. אם אני צריך פה, כדי לקבל אחד, כדי לקבל התפלגות, ובעצם אני סוכם פה, אני עושה אינטגרל על כל הצ'אנלים, על כל ה-x1 עד xn. אוקיי? זה הג'וינט, יש כאן בעצם joint distribution של כל הצ'אנלים, של מ-x1 עד xn. בעצם מה שאנחנו באמת אומרים פה זה f, זה באמת, זה רשום, אבל בעיקרון זה מה הסיכוי של f לקבל בממד הראשון מספר, בממד השני מספר, בממד השלישי מספר, בממד ה-50, עד הממד ה-n מספר מסוים. אוקיי? יש לך, אתה במרחב מאוד מאוד גדול ואתה שואל איפה מה הסיכוי להיות בנקודה במרחב הזה? אז אם יש לך רק ממד אחד, אז זה פשוט המקרה הרגיל של מה הסיכוי להיות בנקודה ספציפית במרחב הזה. אז אני צריך את מספר אחד. אבל בגלל שיש לי כאן n ממדים, ואני רוצה נקודה אחת ספציפית במרחב, אני שואל מה הנקודה,
מתוך ה-n ממדים האלה? זה השאלה?
יש לי n ממדים, ואני רוצה להיות בנקודה אחת בתוך המרחב הענק הזה, ב-n ממדים. אוקיי? לא בממד ספציפי, אני רוצה בממד הראשון להיות ב-2, בממד השלישי ב-3, בממד הרביעי ב-4, וספציפיקציה של כל אחד מהממדים האלה תביא אותי לנקודה אחת במרחב הגדול הזה. נכון? תחשוב על זה כדור. אתה רוצה נקודה אחת בכדור הזה להיות. אתה צריך להגדיר אז מה ציר ה-x שלך ומה ציר y שלך, נכון? כן, וזה שלך. אז בעצם, אז זה בדיוק אותו דבר, אתה יכול לשאול פה זה בעצם מה הסיכוי שאתה תהיה בנקודה אחת בכדור. בנקודה ספציפית בכדור. אז אתה אומר, אתה מגדיר מה הסיכוי שאני אהיה בציר x פה, בציר y פה, בציר z פה. וזה מגדיר לך נקודה במרחב. בסדר? אוקיי? כן. זה פשוט סטנדרטיזציה של משתנה גאוסי. אתה בעצם יכול לקחת כל משתנה גאוסי, x הוא גאוסי, עם איזשהו מיו וסיגמה, ואתה שואל מה ה-CDF שלו, x.
מה ה-CDF שלו?
כן. אז אתה יכול בעצם להגדיר את ה-CDF של x בעזרת CDF של Standard Normal Distribution.
מה זאת אומרת?
סטנדרט נורמל, ההגדרה של זה
זה מיו?
מה זה? זה מיו, כן. כתב שלי נוראי, אני יודע. אם Z, כן, אנחנו אומרים ש-Z הוא Standard Normal Distribution עם 0,1, וה-CDF שלו, F של Z, אנחנו מגדירים את זה בעזרת זה. בסדר? בעזרת פונקציה. איזושהי פונקציה שאני יודע את הערכים שלה. עכשיו יש לך פונקציה, אני יודע את הערכים שלה. כן? לכל מספר שתבין אני יודע להגיד לך את הערכים שלה. אני לא צריך לחשב אותה. מישהו חישב במקומך. ועכשיו אתה מביא לי משתנה חדש, שרק אתה אומר לי שיש לו משתנה נורמלי עם איזשהו מיו וסיגמה. ואז אני אומר לך, נהדר, אני כבר יודע לחשב אותו. אני יודע לחשב את ה-CDF שלו. אני לא צריך לעבוד כדי לחשב אותו. איך אתה מחשב אותו? תוריד את הממוצע, תחלק בסטיית התקן, ואת המספר הזה תכניס לפונקציה שכבר יש לך. פעם אחת חישבת אותה, מישהו חישב לפני 200 שנה, זה יש לך. לא, זה פונקציה ספציפית. זה אני מגדיר, פונקציה.
מה זה פונקציה?
הפונקציה הזאת זה ה-CDF של משתנה גאוסי עם ממוצע 0, סטיית תקן ווריאנס 1. פחות חשוב כרגע, אבל בעיקרון אפשר לזה, אבל בעיקרון אתה יכול, היא נראית משהו, פשוט נראית משהו כזה, כן. זה פונקציה. כן, זה פשוט אינטגרל של גאוסיאן 0,1. ואז בעצם, ואז אתה אומר, אז היופי הוא שאני אומר לך, יופי, חישבת את הפונקציה הזאת פעם אחת, מישהו חישב את הפונקציה הזאת פעם אחת. עכשיו, כל משתנה שתביא לי, כן, אני יכול בעצם זה לא עובר דרך האפס, זה עובר דרך פה, אבל לא חשוב. אבל כל משתנה שתביא לי, כל משתנה גאוס שתביא לי, אתה יכול לחשב בעזרת הפונקציה הזאת. פשוט תנרמל אותו, תוריד אותו ממוצע, תחלק בסטיית התקן, ותכניס את הפונקציה הזאת, תכניס פה מה שיצא לך, הערך שיצא לך, תבדוק ב-values. זה הכל, ומצאת את ה-PDF של, את ה-CDF של X.
כלומר, זה אפשר למצוא את ה-CDF של כל משתנה נורמלי.
בדיוק. כל משתנה נורמלי, אני מוסר לך את ה-CDF, ואני לא צריך לחשב אותו בכלל, כבר חישבתי פעם אחת את זה. וזה קורה כי אני יכול להגדיר כל משתנה נורמלי, אם אני מוריד לכל משתנה נורמלי שאני מוריד לו את הממוצע ומחלק בסטיית התקן, אני הופך אותו למשתנה נורמלי של 0,1. כן. זה... התפלגות גאוסית יש לה המון תכונות מאוד... אנחנו נשתמש גם בהתפלגות גאוסית, כן. כי... במה? גם, כן. זה... גם זה... תחשוב על זה שיש לך איזשהו... נגיד, סתם, אנחנו מבקשים לכם לחשב CDF של איזשהו משתנה. אז אם יש לך איזשהו משתנה כאילו, וצריך ממש לעבוד, אתה צריך לעבוד ממש קשה, ממש לעשות את האינטגרציה הזאת על ה-PDF שלו, נכון? אתה ממש צריך זה, לעשות משתנה מאוד מסובך או זה. אבל אם זה משתנה גאוסי, אתה בכלל לא צריך לעבוד קשה, אתה אפילו לא צריך זה. זה בסך הכל הפונקציה שכולם יודעים את כאילו את הזה של הפונקציה סטנדרטית שכולם יודעים את הפונקציה. כן, בדיוק. זהו. Okay, so hi again. Now we are going to talk about the limit theorem. So suppose that we have xi random variables that are IID with some mean and variance, and we define the empirical mean as sum over all these random variables. Okay? So we have a lot of random variables, and we define the empirical mean of them as their sum, 1 over n, the average of their sum. Now, what is the expected value of the empirical mean? If all of them, if their mean is mu, as it's also mu, and what is the variance of the empirical mean? So let's do it here. It's 1 over n to the square, sum of their variances, and this is equal to sigma to the square divided by n. And we can see that as n goes to infinity, this term goes to 0. Okay? So, so we can see that as n goes to infinity, we converge to the real mean, and it's concentrated around the real mean, and the variance is getting smaller. Okay. So we assume that they have some mean with some variance. Yes, this is our assumption. So, more formally, we say we have the weak law of large numbers. Okay, that if we have xi random variables IID with finite mean and finite variance, then the probability of the empirical mean to be close to the real mean, the probability of this to be smaller than some epsilon goes to 1 as n goes to infinity. Okay, so the probability of this term of the empirical mean to be close to the real mean, the probability of this is smaller than epsilon. The probability of this distance to be smaller than epsilon is it goes to 1. Okay, in high probability we will get the real mean. So this type of convergence is called the convergence in probability, right? So, as I said, we concentrated around the real mean. So now, so we know that we concentrated around the real mean, but what about the whole distribution? How the whole distribution is acting when we have a lot of IID samples. So for this, let's suppose that we have two random variables, x and y, and we want to know two independent random variables, and we want to know what is their sum. Okay, so we have new random variable z that is it equals to x plus y, and now we want to know what is the density function of x. So what is the density function of x? So what? They are just two random variables that are independent. So okay, so suppose that suppose that x is equal to some value k. What we need to require from y? In order, if we want some value for z, okay, if we want f of z for some z, okay. Now we know that x is equal to some value. What we need to require from y? Right. Z minus x, z minus k. So this is one value, right? X is equal to some value k. But we need to go over all the values and to sum all the values. So in the continuous case is just integral. So we just need to go between minus infinity to infinity, f of x, f of y, z minus x dx. Okay? Is it clear? Okay, so this is for two independent random variables. Now let's define, if we have two random variables, let's define the convolution of them. So convolution. So the convolution of x and y is equal to so this is how we convolution is equal to the integral between minus infinity to infinity f of x, f of y, z minus x dx. Okay? This is the definition of convolution. And it's easy to see, of course, that convolution is exactly the sum of these two random variables. Okay, so now let's return to our main question. So suppose that now we have xi samples, and we want to know what is the distribution of their sums. So apparently that the convolution, the Gaussian distribution, is a stable fixed point of convolution. Did you learn dynamic systems? Yes, you know what is a fixed point, stable fixed point attractor, right? Good. So apparently that the Gaussian distribution is an attractor for the convolution. That means that if we are doing small perturbation, if we are doing a lot of small perturbations, we will get to the Gaussian distribution.
You explain what you mean by a fixed point in space, because
Yeah, I will not do it formally. If you want, we can talk later. But basically, if you start from some distribution, and you are doing convolution on convolution and convolution, you are doing a series of convolutions, then you will get to a normal distribution. Okay? No matter what is your initial distribution. So now we want to ask. We have xi samples, and now we want to ask what is the distribution of their sum. So we have x1, x2 plus x2 plus x3 till xn, and we want to know how they are distributed. So we can see that we can take x1 plus x2, and we can sum, and we can get the sum of this value with this value, and we can continue, and then we have a sequence of sums, of summations, and we know that a sequence of that summation is just equal to convolution, right? And a sequence of these summations is equal to a sequence of convolutions. Yeah.
You mean like first they do 1 and 2, and then they do this sum?
Yeah, exactly.
And then
Exactly. 1 plus 2, this term plus 3. This plus.
do you know how many convolutions you need to do in order to get
It goes basically no. It goes as a factor of square root of n. The variance goes like it coming narrower and narrower as a factor of square root of n. Yeah. No, n is the number of steps. It's a function of the number of steps that you are doing, the number of convolutions. So because we know that a series of convolutions, at the end we will come to the Gaussian distribution, then we know exactly that this summation will bring us to Gaussian distribution. So this is the intuition, and this is exactly what the central limit theorem tells us. Central limit theorem. So suppose again that we have xi random variables with finite mean and finite variance. Then the probability of the sample mean minus mu divided by sigma divided by square root of n, this probability goes to normal distribution. This distribution goes to normal distribution as n goes to infinity. Okay? And this type is called also a converge in distribution, because we know the distribution of the converge samples. Okay? So it's very important. What?
Can you repeat the first part? The if part.
So if we have xi IID random variables with finite mean and finite variance, then we know that as n goes to infinity, the distribution of their sum goes to the normal distribution after we normalize it. Okay? So So for example, what basically it says that no matter how the random variable are distributed, if they have finite mean and finite variance, then they will go to normal distribution. Okay. That's it for central limit. Now let's talk about what you already saw in class. So deciding between two world states. Okay? So now let's suppose that our sample space is omega 1 and omega 0. We have two possibilities for our world. And age 0 is, we have age 0 and age 1. Age 0 is that the true state of the world is W0, and age 1 is that the true state of the world is W1. And now, as you saw in class, so we need to decide, we have some observation on the world, and we need to decide what is the state of the world. We need to decide alpha 1, alpha 0, or alpha 1. Okay? What is our action? We need to decide. We assume that we all know that this is the state of the world, or this is the state of the world. Okay? And we also have the cost function. So our cost function for I, j between 0 and 1. Okay, we have some cost function. So the lambda ij is the cost that I need to pay if I decided alpha I and the true state of the world is wj. Okay? Great. And as you saw in class, the likelihood ratio test with some parameter theta is a decision rule that basically say we see some observations on the world, and now we want to decide. So how we decided? So we decide if p of x given w0 divided by p of x given w1 is greater than some threshold. So if this is true, we will decide alpha 0, and if it's false, we will decide alpha 1. Okay, this is the likelihood ratio test. And if we are Bayesian, if we have some priors on the world, so we know that the optimal test is just set theta to p of w1 divided by p of w0 times lambda 0, 1 minus lambda 1, 1 divided by lambda 1, 0 minus lambda 0, 0. Okay? This is the optimal threshold. If we have priors on the world. Okay? Yeah.
we compared between two risks, and then we came up with this ratio.
Yeah.
So this what makes it, this is why you say it's the optimal.
Yeah, because you can set this for the risks. Okay, so if we say this in the risk, you will get the same thing. But also, of course, if we don't have priors on our world, we can say we can define some theta and just put it in this likelihood ratio test and decide this or this, alpha 0 or alpha 1. Yeah.
Why make why this is equal to the upper ratio, right?
What? This?
Maybe I
Okay.
I could do that.
Okay, so come right here, no problem. So now, so given some threshold theta, we can divide our world or our sample to two regions. Okay, D0 is all the values of x, all the observations that we get, that we will say that the world is H0. So all the observations that the likelihood ratio term is equal then theta. Okay? And we can also define D1 is all the observations that the likelihood ratio test is smaller than theta. Okay? So given an observation, we can decide what is if the likelihood ratio test is bigger or smaller than theta, and these decisions split our world to two regions. Okay, so now we can define two types of errors. So we have type 1 of error. So a second. Okay, so we have two types of error. Type 1. Type 1 is the false positive. What does it mean? That, okay, so it means that the true state of the world is W0, but I decided W1. I decided that it's W1, right? So it's the same thing as to say that, let's denote it by alpha of omega, and this is equal to the probability that x is in D1 given that the true state of the world is W0. Okay? I got the probability that I will get something that is in D1, so I will decide that the real state, I will decide that the state of the world is W1, but the true state of the world is W0. So this is false positive, and we also have false negative, type 2, that we'll denote it by beta, is the probability that x is in D2, but the true state of the world is W1. Okay? Is it clear? So now let's do a simple example. Sorry. Yeah, it's D0. Sorry. This is D1. This is D0. Okay. So let's do a simple example. So now we have a Bayesian decision problem. So x, we know that x given W0 is Gaussian with 0 mean and variance 1, and x given W1 is Gaussian with 1 and 1. Okay? And suppose their priors are equal to 0.5. Now let's suppose that the cost function this is lambda ij is equal to 1 minus delta ij. That means that if it's the right decision, it's 0. If it's the wrong decision, it's 1. Okay? Do you know delta ij? What does it? And now we want to ask what is the decision boundary of this. Okay? So how does it look? We have two Gaussian, one Gaussian, and second one. This is 0 and this is 1. Okay? And so we have some decision boundary here, and this is D1 and this is D0. Okay, if we get samples in this region, we will decide alpha 0, or in this region we will decide alpha 1. Okay? And now we want to ask ourselves, okay, so what is X? What is the decision boundary? So, how can we do it? Yeah, how can we find the intersection? See? What? So, right. We need to calculate the log likelihood, right? So the log likelihood we need to compare it to theta, right? So what is the log likelihood in this case? The log likelihood is just, by definition, is a P of x given W0 divided by P of x given W1. Okay? So in our case, we have E minus x to the power of 2 divided by 2 divided by E minus x minus 1 to the power of 2 divided by 2, right? This is f of x given W0 divided by f of x given W1. Okay? This is the log likelihood ratio. And we compare it to some theta. So we can take the log out, we can take log of it and to reorder it, and we will get that minus x to the square minus x minus 1 to the square divided by 2 is greater than log theta, or that x is not greater than log 1 over theta plus half. Okay? So what we did here is to change from a term on theta to some inequality on X. So this exactly defined our regions. When X is smaller than some, when from this term we will decide something, and if it's bigger than this term, we will decide we'll decide alpha 1. Okay? Is it clear? Great. So D0 is between minus infinity to this term. So now let's, if we will substitute in the optimal omega our priors and the cost function, we will get that omega is equal to 1. Okay, just substitute in the optimal theta, and then all of this term is equal to 0.5. So D0 is between minus infinity to 0.5, and D1 is between 0.5 to infinity. Yes, I just substitute theta is 1, and theta is 1 because the prior are equal, and we have the cost function of 1 minus delta.
How do you know the prior?
I just assume that they are equal. You can check it. It's interesting to check what happens if we change the prior, how it's effect on the decision boundaries. So in this case, X here, the decision boundary is 0.5, exactly in the middle of the two means. Okay. Now let's find the alpha. So how can we find alpha? What is alpha? What is the definition of alpha? So we need to take integral over all the possible values of when X is in D1. What is inside the integral? What we need to sum over? F of X given it's W0, right? It's the probability that we will decide that we will get X that is in D1, but we will decide something else. Okay? The true state of the world is W0, but we will get something that we will decide that it's in the true world state is W1. Okay? And you can you just can substitute this. We know already that it's a Gaussian, and we will get 1 over square root of 2 pi, the integral between 0.5, right? Because theta, the decision boundary, X is the decision boundary X is 0.5, so we need to take the integral between 0.5 to infinity, e to the minus x to the square divided by 2 dx. Okay, and you can do the calculation, but you will find that it's equal to 1 minus the standard normal, the CDF of the standard normal distribution of half. Okay? This is the CDF of the standard normal distribution, as we saw in the last hour. Is it clear? Questions? Okay. And in the same way, you can find the beta, but you need to integrate over B0, and here you will have f of x given W1.
Is this happening?
Yeah.
Wasn't it supposed to be a variable inside the...
Why? Variable of what?
It says phi of z before. Maybe I'm confused.
You don't have here basically it's a function of theta, but we already set theta to some value, and then we set x. We have a specific boundary x that is not a random variable. It's just a specific value. It's 0.5. Okay. Where do you find here?
This is a normal distribution.
Yeah. This is normal distribution, standard normal distribution.
Okay, the variable. It's a distribution that should be a...
No, it's the CDF. It's the standard normal distribution looks something like that. Okay, and so this is just the value of this function in 0.5. It's a number. Okay. Okay. So now let's. We have time. Yeah. Okay. So now let's do another example. Okay, now let's assume again that we have two world states, W0 and W1, and x given Wi is distributed as exponential distribution with the parameter lambda I. Okay, and let's assume that lambda 1 is greater than lambda 0. Okay, now we want to find the decision boundary and also find beta. So how can we do it? Again, what we need to do, exactly, we need to convert from the likelihood, right, from the likelihood to some term on x, on the observation. So we know that f of x given Wi is equal to lambda I e minus lambda ix. Okay, this is the definition of the exponential distribution with this parameter. And so the likelihood ratio test. So the likelihood ratio is equal to lambda 0 divided by lambda 1 e to the power of lambda 1 minus lambda 0 x. And this is at least theta. Okay? And you can take the log of this, and we will get that log of W0 divided lambda 0 divided by lambda 1 plus lambda 1 minus lambda 0 lambda 0 x is at least log theta, sorry, and we get that x is at least 1 over lambda 1 minus lambda 0 log log of theta lambda 1 over lambda 0. Okay, so we get x we got some boundary on x, and this is just a function of theta, right? This is lambda 1 and lambda 0 are constants, and this is just function of theta, so it's just a function of theta. So we don't have a lot of time, but so let's start with intuition. So we have here this is P of x given lambda 1, W1. This is lambda 1, and here we have P of x given lambda W0. Okay, so we have these two functions, and we say that when x is bigger than this term, we will decide it will be d0, right? So we have here some value that from this value we will decide d0, and between this to this value we will decide this will be d0. If we will get examples or observation in this region, we will decide alpha 0, and if we will get examples from this region, we will decide alpha 1. What? This is t. It's just a function of theta. It's important that the decision boundary is a function of theta. Okay? So, what is beta? What is beta? Integral between. Where is beta here? No, when we will decide beta, when we will get wrong.
The area of
It's okay. Exactly. We will decide this 0, but right. So it's exactly this area. Okay.